So on the worksheet that I gave you that you can find in SI Resources, or you have a copy of it right here, the first page has the formulas that I think that you would need and a little other important information. And so I guess it's possible, depending on your instructions, you might not be able to use it because it's got like words and diagrams and stuff. But I do have the first things I have are the basic non-inverting amplifier. So if you have an amplifier that just looks like that, you know what the gain is. It's 1 plus R2 over R1. So if you have something simple like that, it's not likely to be just like that, but it's possible it could be. And then this is the inverting amplifier, and you can see that the gain is negative. And we'll be working on, we have a couple of op-amp problems to do. These formulas are for ideal op-amps. They're the golden rules for ideal op-amps. That VP has to equal VN. That's the positive. Do y'all use PN or plus or minus? Plus or minus. Okay, so that's V plus equals V minus. That the voltage at the positive terminal has to equal the voltage at the negative terminal. It does not have to be zero though. Unlike the current, I plus has to equal I minus has to equal zero. So you can't have any current flowing into either terminal of the op-amp, and you're going to use those to solve the op-amp problems. You also have the basic formulas for a capacitor. So these first three here are for if you have just a capacitor. This is not an RC circuit. You just have a capacitor that you're charging or discharging. And you'll use these when you have the problems that have the graph, and you have to like take the graph and from that find information. This is the sort of thing that you'll use that for. And we have the voltage as a function of time. Is given by this interval. The current for a capacitor is C dV/dt. The power for anything is V times I, and since I is C dV/dt, this will be C times V dV/dt. If you are looking for it, capacitors in series add like resistors in parallel. So if you have two capacitors in series, it's you can use product over sum. If you had more capacitors in series than just two, you can't use product over sum. So if I had if I had multiple capacitors in series, then what I would do is so let's say I had three capacitors. The equivalent capacitance would be 1 over C1 plus 1 over C2 plus 1 over C3 and so on. But if you just have two, you can do product over sum. Capacitors in parallel add like resistors in series. You just add them up. The energy for a capacitor is 1/2 CV squared. You'll probably have to find the energy for either a capacitor or an inductor somewhere. And what's important for doing the capacitor problems, when you are trying to find out what the circuits are like at different times, is under DC conditions. This means when they've been sitting there for a long time, they act like open circuits. And what's really important about them is they can't change voltage instantaneously. They can change current instantaneously. And then I have the similar formulas for inductors, but inductors add like resistors. So inductors in series, you just add them together, and in parallel they do product over sum. So inductors add like resistors. And under DC conditions, inductors act as short circuits. And they can't change current instantaneously. They can change voltage instantaneously, but not current. These are the two equations that you'll use when you have to find a function for an RC or RL circuit. They're the same just for capacitors. You have V, and for inductors you have I, and the time constants are different. To find the R equivalent for the time constant, you're going to find it's R Thevenin, and you short voltage sources, and you make current sources open circuits, and you find the resistance as seen by the capacitor or the inductor. So that's your formula sheet, that's what you've got on there, that's your basic concepts. And after I answer any questions on that, we'll start with the problem. So any questions on any of these formulas? And of course, for some reason, they thought it was a good idea to put a column right in the middle of this room. So, I can't see a lot of you. But, any questions? Anything on that? Okay. All right. Nothing urgent. All right. I will go on to problem one.
Is the column low?
Probably. I don't think they were too concerned about things looking too nice in this building. Actually, I am just going to go ahead and